No bloco de notas de hoje, nós temos mais uma entrevista da série em parceria com a Escola de Verão em Química da UFSCar, que em 2020 está na sua 40ª edição. Na edição de hoje eu converso com o professor Markus Rose, da Technische Universität Darmstadt, da Alemanha. Professor, thank you very much for your time. It's a pleasure talking to you today.
It's a pleasure for me too. Thank you.
You are a professor in chemical technology.
Yeah.
What are we talking about when, although it seems obvious, okay, chemical technology, but what is chemical technology?
Oh, actually, chemical technology is kind of a German thing. When you study chemistry in Germany, you can have in the master's studies further on a focus on more engineering-related questions. So you become kind of half an engineer. A chemical engineer. And chemical technology, as the name proposes, combines both worlds. We have a basic chemical education and also a basic engineering education, and that is combined. So our students, when they focus or major in chemical technology, they are able in the end to communicate also to chemical engineers. And that's very important for all people who go to the chemical industry on a job later on. Where they talk to each other on a daily basis. So the scientists and the engineers, the chemists and the process engineers.
So these professionals, it's thought that they can help in this communication.
Yes, not only for the communication, but I mean, chemical science is significantly different from engineering sciences. For example, a chemist knows how to work in the lab. He has all the knowledge and the features to do lab chemistry, while the engineer knows how to build a big chemical plant at the end, but they often lack the ability to do chemistry in the lab. And it's important to at least know a little bit of the other side, to know what they are doing, and this is what we try to teach them.
And your research group is presented with a sentence which is where sustainable chemistry and materials design meets catalysis engineering.
Yes.
I would like you to explain each one of these activities or ideas like sustainable chemistry, materials design and catalysis engineering, and how do they meet in your research group?
Okay, I will try. That's a long story. So the sustainable chemistry, I mean, that's nothing you can study, right? But sustainability today is a very big word. A word is often used and often sometimes also misused. It just refers to something that we want to develop a chemistry and a chemical industry that can produce products, fuels, energy and everything in a sustainable manner, so that can go on like forever without wasting resources. And that is one of the major points, the resource question. Our industry is based on fossil resources, oil, coal and gas, and there is an alternative, something renewable like biomass. And that is often, when chemists talk about sustainable chemistry, they typically mean using alternative resources. And the chemists try to exploit ways how to convert biomass to something useful. And that is actually the sustainable chemistry part. The materials design part, that is a little bit based on my background during PhD time, because there I was not focusing on the sustainable chemistry. There I was making new materials for catalytic applications. I'll come to the catalysis in the next keyword. And there we focused on interesting new materials that have very special functions, that they can do stuff, they can convert chemicals. And we developed new of these materials. And actually the materials design means we had ideas and used chemical routes, chemical synthesis to produce these new materials. And then both words combined, I tried to combine during the last years when I became professor in chemical technology, and I was interested in the biomass conversion, but I also wanted to continue to work with these nice functional materials. And this is actually what the catalysis engineering is about. So catalysis is what we use the materials for to convert the biomass to something useful. So the catalysis engineering now tries to combine the best of both worlds, basically. So the sustainable chemistry, where we try to convert biomass and renewable resources. And for that we need new materials, new catalysts. That's why catalysis development is very important. And the engineering aspect, actually, that is what I mentioned earlier, that we try to combine chemistry and the engineering, that because many chemists do not only think about the lab chemistry, and there's a lot of engineering aspects to lab chemistry that is often overseen, and we try to think these things from the beginning. And that is why we, in the end, when we do our lab chemistry, we already have like a final industrial process in mind and try to work towards that. And that is meant by catalysis engineering, combining lab chemistry in a very small scale on a molecular level up to a chemical plant on a large scale level.
Okay, and one of your focuses is a special class of materials, that is porous materials. Of course, we can understand what porous is, but what are porous materials used for? Why is it important to do research about them? And if you can give us some examples of your research work.
Okay, so first we have the type of porous we refer to. Imagine a foam. You can squeeze a foam, right? There's a lot of air inside, or water. It can take up water. And if you decrease the size of these pores, make them very, very tiny, so tiny that you have nanometer-sized pores, like in the size of a molecule, then you have a huge surface area in the materials. Imagine like a sugar cube, like one square or cubic centimeter of sugar that has a surface area of 1,000 square meters inside in these small pores. And this is the type of porous materials we refer to, because we need these high surface areas.
It's not a sieve then?
Kind of a sieve. People call them molecular sieves, actually. You can sieve molecules with this. This is also one thing they are used for. For a long time, there are like minerals out there which act like these sieves, so-called zeolites. They can be used in catalysis. We use them as well. And then there are activated carbons. Many people know from, let's say, home applications, in filters, in water filters, there's an activated carbon in there. That's also one of those highly porous, high surface area materials. And this is the type of materials we typically work with for the catalysis.
In 2017, you've received an innovation award from the University of Aachen. And that was for a project with the production of monomers from renewable resources. Would you tell us a bit about this work?
Sure. This was actually based on a collaboration with industry, with Europe's largest sugar producer, Südzucker. And we came with an idea to them for producing a monomer, to build a polymer, a plastic, out of sugar molecules. And the thing is that the sugar molecules, they have functional groups. It can be an alcohol. It was an alcohol in that case. And these alcohols can be transformed into something more useful called an amine. And this amination step, making an alcohol to an amine group, this is a catalytic step. We tried to improve, or we tried to find a shortcut way in one reactor, getting from the sugar to this amine by a technique that's called catalytic amination. We needed a catalyst for that. It was done in water, because water and sugar, they behave well, so the sugar can be dissolved. And then you need another chemical, ammonia, a gas. And in high pressure reactors, we can convert then the sugar to the amine, to the monomer. And actually, the development of this technology, we filed a patent on that, which was granted in several countries already. And currently, we try to develop this technology further. Now we go for the engineering aspects. Before we did the chemistry, now the engineering. And for this technology, we were awarded this prize at my old university.
And why building plastic from sugar?
That goes back to the sustainable chemistry part. I mean, bioplastics is a big topic. Plastics are in the media everywhere for all the plastic waste that is floating around. And there are two strategies that you can follow. You can you have to have a good recycling of plastics, of course. Or you make plastics biodegradable, that they do not stay in nature for a long time, but they decompose. Or you use other resources to produce these plastics, like biomass. Then it's not made from fossils, from oil. All our polymers we use nowadays, mostly all, are based on oil-based products. That's also what I teach here in the course in the summer school, actually. And And this is one of the major reasons we look into the production of monomers from renewables, because then we could get out of the carbon cycle of the fossils and develop a new carbon cycle which is renewable. Yeah? Plastic can be converted in the worst case to CO2 that goes to the atmosphere. Later on, it's bound by plants again, and the biomass is then fed again to the chemical industry, which converts biomass.
And it is from sugar or from sugarcane? It's really from sugar already.
In Europe, we don't use only tiny amounts of each from sugar beet actually in Europe. And the sugar you get out there that you can eat, that is one of the precursors, one of the substrates that they use. But actually what we converted to these amines, it's a follow-up product, but which is also commercial already. It's called isosorbide. There's some pharma products based on that already. But it's one of the potential, very high potential monomers in my view. That I think there will be some polymers in the near future. There's a Japanese company which already set up one of those polymers, it was 1 or 2 years ago, and it's apparently in high performance materials in smartphone covers. In one special type of smartphone, they sell it already. That was amazing for us to see that there is another product, not ours, but another product going in a nice biopolymer for functional material.
Okay. Now I have a last question, and I've asked your colleagues too, and that is what, if you remember your first, how did you first meet science? Oh. And how did you decide to be a scientist?
Oh, this is a very good question. Actually, it has a lot to do with my father. So he's not the chemist, but he's working in agricultural industry, basically. And when I was a very little child, he studied next to his job something like agricultural chemistry. And he was always telling at home stories and stuff from plant chemistry and so on. And at that time, I already got interested in the topic. And then I had access to his textbooks, to his chemistry textbooks. And after preschool, when I was able to read well enough, I had no idea about chemistry, but I was reading these textbooks. And and then it developed the interest for chemistry especially. And in Germany, we start chemistry in school in the 7th grade, like at the age of 13 maybe. And at that time, I had already done some experiments at home, like what you do typically as a child when you get one of those chemical starter boxes, and then you do first experiments. And then there was another thing, my father, due to the plant chemistry, he always mentioned a famous old German chemist from the 18th century, Justus Liebig. And that was so burned into my head, the name and the story behind that. We even named our son after him. It was a little crazy maybe, but it was funny. No, but it was really from childhood on. I did experiments at home, sometimes with fire, sometimes without, bubbling stuff, everything you can do with simple chemistry kits.
Okay, thank you very much.
You're welcome.
I've learned many things, and it's been overall a great pleasure. Thank you.
Thank you very much.
Esse foi mais um bloco de notas. Quem se interessou pelo trabalho do professor Marcos pode visitar o site do grupo de pesquisa e a gente se vê no próximo bloco de notas.